Hello, pre-calc. Just kidding. Hey, stat. Let's look at what we were reviewing today. We had a couple more to do, so I didn't want to leave you in the lurch for tomorrow's test. So actually, I think I'll pick it up on review question number 10, even though we did that one. Because when I got to 11, some of you didn't look comfortable with the results. And I want to change a little something about 11, not the concept, but the actual number that we used. So let's pick it up here where we have this table, and it's a random variable. The possibilities are a profit of 1 million, 2 million, 4 million, and 10 million. And here are the probabilities of those happening. You notice they add up to 1, the probabilities. Now, we were asked to find the mean. And you recall when it's not a binomial random variable or anything special, you find the mean like this. It's also called the expected value. So if you see the word expected, they're just looking for the mean. So it is always going to be whatever possibilities, like one possible outcome, 1 times the probability of that outcome, plus the second one and the probability of that outcome, etc. So we did that in class. So we had one outcome times 0.2 plus the second outcome is 2. It had a 0.5 probability of happening. Then we have 4 times 0.2. And we had 10 times 0.1. And when we added that all up, I believe we got a 3. So I'm going to go with that. So that's the expected value. So over time, the company is expecting to make 3 million. All right, so with that, that's expected value or the mean. Then we had to actually use that down here, but I didn't use it. Because we were talking about the company in number 10. If you recall, I made up some kind of mean. I knew we needed a mean, but I didn't recognize we were supposed to grab the mean from the previous problem. So we're going to need that. So, and the standard deviation is you take each outcome that's possible, subtract the mean, and square it and multiply it times the probability of it happening for each value. So for example, the first possible outcome is a 1 minus the mean. Square that. Oh, actually, I'm looking for a standard deviation. So actually what I'm doing here is the variance. So I'll put a little squared there to remind you that this is actually the variance. And what reminded me was this little squared thing times the probability is 0.2 plus the second possible outcome is 2 minus the mean times its probability of happening 0.5. These are all multiplied in each term. Then the terms are added. And 4 is the next possible outcome minus the mean squared times the probability of that happening, 0.2. And lastly, 10 minus the mean quantity squared times the probability of that happening. So when I added all that up, I don't remember what we got, and I hope we handled it well because that's 6.4, but that is the variance, and this is asking for the standard deviation. This formula is the variance. So if I didn't mention that in class, I don't remember mentioning it. We have to actually take the square root after this procedure, so make note of that. And it comes out to 2.53 for the standard deviation, which we may need down here. So on 11, this is where we end it in class, but I'm going to review this again. Say that the company in number 10, so this mean and this standard deviation are in play in this problem, which I didn't pick up on in class. It turns out the company doesn't get all this money. It only gets 90% of the profit. Maybe it donates 10%. And it pays a capital fee, what's the word fee here, of 200,000. We're going to work in mils, so we'll call it 0.2 mil. So I'm going to make a linear combination. So the y, the amount that is the actual money retained, is going to be 0.9 times the profit from up here minus 0.2 for the fees. So this is a linear combination when not only do we multiply the variable by something, then we subtract from it. So what we learned in that day 3, a linear transformation, linear combination, to find the mean, how is the mean affected when we actually take a random variable and multiply and add or subtract? It is actually affected by both operations. So we're going to grab the old mean of 3. And so the mean of y is going to be the old mean, which is 3, times the 0.9 minus the 0.2. And when I multiply that together, I get 2.5 mil for the expected mean of this random variable, which is a linear combination involving this random variable. Standard deviation of the linear combination we learned, and it also correlated to what we learned earlier in chapter 3 or 2. When the to find the standard deviation, when a random variable is both multiplied and subtracted or added, only one of these operations will affect the actual standard deviation, and it's this one that does not affect it. Adding or subtracting, when we move a random variable by addition and this one's subtraction, you'll notice the spread of my fingers is the same, so it's not affected by adding and subtracting. But when we multiply, everything spreads out, so the standard deviation will be affected by that. So I'm going to take the old standard deviation and multiply it times the 0.9. But I'm not going to address the fact that something has been added or subtracted because that does not affect the spread. So this is all we have to do. And Bree, I think you were right when you said the absolute value of, the absolute value of B. I remember now. I should have listened to you. So you were right, only the multiplication will affect it, and if this happens to be negative, I don't think we've ever seen a problem where it is. We do have to use an absolute value of that number. So it doesn't usually affect our results, but I guess it could. I don't think they did that on the test, so. Alright, so that comes out to 2.28. I hope. If I calculate anything wrong, notify me before the test and I'll clear that up. Alright, let's go back to number 12 where we do not have, we haven't gone over this one at all. So, alright, I've asked you to try it before you actually look at the video, so I hope that you have been able to do that so you can benefit more than just doing it with me. The length of human pregnancies are normally distributed, so we don't have to test for it or anything. It's just given to us. Here's the mean of a human pregnancy, and here's the standard deviation. And X and Y are two randomly chosen pregnancies. So we just got two pregnancies going. Find the expected difference between the two. This one's a little tricky because it doesn't tell you if they want X minus Y or Y minus X. So we're going to have to do both and add. So I'm going to find the difference as X minus Y on this side. And over here I'm going to find the difference as Y minus X. Because it didn't say. It just said find the expected difference. When I see the word expected, even though pregnancies talk about expecting. This is not that kind of expecting. This is the mean. So whenever you see the word expected, you want the mean of the difference. So I'm looking for the mean of the difference. So I'll indicate it with that. Let's see if it shows up a little better. The mean of the difference is what this points to. And I could also call it the expected value of the difference. So sometimes we think of it like that. So we are looking at the difference of two random variables. So we learned that we can get the mean of the difference by just taking the two individual means and subtracting them. So looking up there, it says we have two randomly chosen pregnancies. So the mean of the first one, the first chosen pregnancy, is 226. And that doesn't change when you pick another pregnancy. So Y is another randomly chosen pregnancy, but the mean is still 266. So when I subtract 266 and 266, I get 0. That is the expected value of the difference. But since they didn't say, did I mean x minus y or y minus x, I'm going to do both of them to cover my basis. So this one, I'm going to do the expected value of the y pregnancy minus the expected value for the x. But any human pregnancy, according to this data, has a mean of 266 days minus 266 days, so I get 0 again. So that's how I handled that one. All right, let's look down at part B, the standard deviation of the difference. So that's where we get in to special thinking. So I'm going to do it in two cases. I'm going to do the difference is defined as x minus y. And over here I'm going to do the difference is defined as y minus x. In case you're in the situation like that. We're looking for the standard deviation. We can't just go up and add standard deviations or subtract them like you might expect, but we can work with the variance. So we can say that the variance of the difference is going to equal the variance of the x random variable minus the variance of the y. So we are allowed to do that, except I did something wrong. And when we have a difference, we actually end up adding. And if we look back on our example with Pete and Aaron and the Jeep tours, you'll remember why that was. So now that we'll get this value, and you can see we can easily get to this value by taking the square root. So I'll get this value first. So going back up here, I see every human pregnancy has a standard deviation of 16. So x and y have the same standard deviation. When I add those squared, I get 512. But the question asks for the standard deviation, so I'm going to find that by the square root. And that's 22.6 days. All right, over here, I'm doing it the other way. I think you will see, looking at this work, now I'm going to have the standard deviation of y squared plus x squared. I'm going to have these same numbers. I'm going to have that number. I'm going to square root it. So the difference is also 22.6 days. All right. In this case, they turned out the same. All right. Let's see what happens on part C. Find the probability that the difference in the two pregnancy lengths is greater than 25. All right, so this time it's really going to count, because once again it doesn't say pregnancy x minus y. It doesn't say y minus x. It just says the difference. So I'm going to define the difference as x minus y over here and the difference as y minus x over here. And since they're looking for a probability, it could be either one, so this or this, which means the word or, when you talk about probability, means to add. So I'm going to find the probability here and the probability here and actually add them together. So the number of interest is 25. So I'm going to come up with a z-score. And we already came up with, we're going to take the 25. What's the mean of the difference? Well, we did it up here on part A. The mean of the difference was 0 in both cases. So I'll do this one first, 0. And the standard deviation in both cases was 22.6. So I'm standardizing or finding the z-score. That comes out to 1.1. Chart A we go. It gave me 0.8643, and the question is greater than. So remember, the chart A is always less than, so we do the 1 minus 0.8643, and we get 0.1357. Will that change over here? Well, let's see. Y minus x, still greater than 5, so we have 25 minus, the y minus x was 0. All right, so we're messing with the same numbers. So we're going to get 1.1, then we're going to go chart A, we're going to put 0.8643, and we're going to do 1 minus 0.8643, and we're going to get 0.1357. The only thing is now, like I said, because this or this meets this conditions, the probability that the two differences, or probability that the difference in the two, so this one is the probability of x minus y being greater than 25, and this is the probability of y minus x. Both of those meet the requirements of the problem, so I'm going to have to add these two. So that's a little tricky. So when I add 0.1357 and 0.1357, the final answer, when I add those two, was about 0.27, and that is the correct answer. So, all right, be able to recreate that in a similar scenario. Pete has 70% chance of hitting the bullseye in darts, and we're going to assume each throw is independent. Pete throws until he hits the bullseye. Find the probability of getting the first bullseye on the third throw. So we are finding that this is geometric. You can switch to the geometric formula. However, I find these so much easier just to do the probabilities. So what I do for this, it says 3 throws. So he's going to miss, and get it. So it says get it. We want the probability that he hits it on the third. So this will be fail, fail, got it. So what's the probability of failing if the probability of hitting the bullseye is 0.7? 0.3 and 0.3, and then obtaining it is 0.7. So those are easy peasy. 0.063. There is a formula that I drug out of you after the birthday game, and if you plug the values into it, you will see it is going to give you the same thing. All right, what's the probability Pete hits 5 or fewer on 10 attempts? So on 10 attempts, now because we've defined the number, it's a binomial. Do you see the difference? Here we were wondering when he was going to get the first success. But here we have a number of trials, 10, and we were wondering what's the probability that he hits 5 or fewer. So it's a binomial. The probability of x is less than or equal to 5. Let's go to the calculator. Second VARS distribution, binomial. Is that a CDF or a PDF? Binom CDF, binom CDF. and you have to tell it the number of trials, which in this case there are 10, the probability of success, 0.7, and the value that we're interested in, 5. Will the calculator give us this value, or are we going to have to alter it? We are going to accept it because the calculator gives us less than or equal to, which matches our problem. So if you put that in, you will see it is 0.1503. All right. Pete forgets his glasses and claims it has no effect on his first 10 shots. So once again, we have 10 shots. We're in binomial land. He hits 5 bullseyes. And is there evidence that his glasses are important? So let's find the probability of that happening. And if it's very, very, very low, then we would say that the chances of him doing that badly are so low that we are going to assume his glasses are important. So we want the probability, again it's a binomial, that he hits 5, so we have x equals 5. Very similar to what we did here, except it says he hits 5. So we're going to do a binomial PDF, and same numbers, 10 trials, 0.7% probability of success, the number equals 5, and we get 0.103. So that, would you say his glasses are important? That is like a 10% chance of happening. So 1 out of 10 times that could happen. So I'm thinking that on the basis of that information, I'm not ready to say that his glasses are important. So I'd say no, because 1 out of 10. Now you could say, that's pretty rare, 1 out of 10, so his glasses are important. So you could defend it your own way. Don't you hate when that happens? All right, number 14, the random variable x is the weight of the black bears. X is normally distributed with mean 250, standard deviation 50. Find the probability x is greater than 325. So since it's normal, we need a z-score for any kind of probability. We're going to take the value we're interested in, 325, subtract the mean, divide by the standard deviation. When we do that, I got a 1.5. Let's go to chart A. And get 0.9332. As we discussed earlier, chart A always gives us less than or equal to the value of interest, and we want greater than. So we have to do 1 minus to get the complement of that. And it's 0.0668, so about 6.7% of the black bears are greater, not that many are that greater than 350, I'm sorry, yeah, 325 pounds. All right, the only other closing comment, I did look through a good study tip is at the end of each section, right before the problem set. So at the end of 6.1, the reading, and before the problem set for 6.1, there is a very good summary. And then there's one at 6.2 and 6.3. They're very short and concise. I recommend that you read that. And I did read over it, and I did notice one thing we didn't mention today, although we did a pretty good job of mentioning everything. By the end of the class, we had most of the important points on the board, but one of them was the difference between a discrete random variable and a continuous random variable. So there are gaps in between the possible solution, or possibilities, we'll say. So for example, what's a discrete random variable. Oh, I know our famous one is the APGAR scores. So you could have one, 2, 3, up to 10 as an APGAR score, and nothing in between. So you were assigned one of those numbers. So there's gaps between 1 and 2. You're not going to be able to score a 2.5 if I understand APGAR correctly. A continuous random variable, however, would be something like, let's say it's the height of the girls in our class. So there's really an infinite number of heights that you could have, because you could have someone who is 5'2", someone that's 5'2" and 1/16 inch, and so there's an infinite number of possible results when you're looking at heights. So therefore, all the results fall within an interval, and it has an infinite number of possibilities. So be able to recognize the difference between a discrete and a continuous random variable. All right, it's been sweet talking to you all. So, as we used to say, study well and carry on.